Good morning, my dear students. How are you today? I hope that you are doing great. Okay, so today we're gonna continue chapter 4, chemical reactions, and we're gonna deal with part 8, determination of the mass of the reactant remaining in excess. The objectives are 1. Determine the mass of the reactant remaining in excess. Recall. In a chemical reaction, when we have two given amounts of the reactants, then the reactants mixture might be either in a stoichiometric proportion or in a non-stoichiometric proportion. If the ratio of the reactants are equal, so the reactants are in stoichiometry where both reactants are limiting reactants, hence all the initial given amounts of each reactant react completely and 0 mole of the initial amount is left. If the ratio of the reactants are not equal, so the reactants are in non-stoichiometry where we have there is a limiting reactant whose initial amount, small n initial, reacts completely, so 0 mole of it is left after the reaction, and it's the one that has the smaller ratio. And there is a reactant in excess whose initial amount, n initial, doesn't react completely, therefore part of it reacts by stoichiometry, n reacted, okay, and part of it remains unreacted, small n unreacted, and is overleft and appears with the products when the reaction is over, that is, after the reaction, and it's the one that has the greater ratio. Objective number 1. Determine the mass of the reactant remaining in excess. To determine the mass of the reactant remaining in excess, also called mass unreacted or mass overleft, it's very simple. First, we find the number of moles, small n, remaining in excess by applying the following rule. Number of moles small n unreacted of the reactant in excess is equal to the number of mole initially found of the reactant in excess in the given, okay, minus number of mole reacted of the reactant in excess. Because as you know, the initial amount of the reactant in excess is not totally reacted. Part of it reacts by stoichiometry and part of it remains unreacted. So to calculate the number of moles unreacted of the reactant in excess, simply we apply this rule. Number of mole unreacted equal number of mole initially found minus number of mole reacted. How to calculate now the number of mole reacted of the reactant in excess? It's very simple. We calculate this by using the stoichiometric ratio, where we have the number of mole reacted of the limiting reactant over the stoichiometric coefficient equal number of mole reacted of the reactant in excess over its stoichiometric coefficient. And always remember that the number of mole reacted of the limiting reactant, okay, is equal to the number of mole initially found of that limiting reactant. Why? Because the limiting reactant is totally consumed and 0 mole of it is overleft. So always when we have a non-stoichiometric proportion where we have a limiting reactant and a reactant in excess, always remember that the number of mole reacted of the limiting reactant is the same as the initial number of mole of that limiting reactant. Okay, it's equal to the number of mole initially found because the limiting reactant is totally consumed. Okay, when this we have this number of mole of the limiting reactant reacted, which is equal to the initial number of mole, it's given. Okay, the stoichiometric coefficient are given, so we can easily calculate the number of mole reacted of the reactant in excess by applying just the stoichiometric ratio. Now, after we have found number of mole reacted, we can find the number of mole unreacted, which is equal to the number of mole initially found, okay, which is given in the given amounts, minus the number of mole reacted, which we have just found by using the stoichiometric ratio. So now, once we have found the number of mole unreacted of the reactant in excess, we can find the mass unreacted of the reactant in excess by applying the formula, okay, mass unreacted equal number of mole unreacted times the molar mass of the reactant in excess, where small m is the mass, small n is the number of mole, and capital M is the molar mass. Now we have an application about stoichiometry. Consider the following chemical reaction. PbNO3 taken twice aqueous plus 2Ki aqueous. It produces PbI2 solid, which means here precipitate, plus 2KNO3 aqueous. Given that 33.1 gram of PbNO3 taken twice are added to 16.6 grams of Ki to form a yellow precipitate and an aqueous solution of KNO3. Of course, the yellow precipitate is PbI2 and it's shown by this small s, okay? Question number 1. Calculate the initial number of moles. Question number 2. Identify whether the reactants are in a stoichiometric or non-stoichiometric mixture. Question 3. Identify the limiting reactant and the reactant in excess. Question 4. Determine the mass of the reactant remaining in excess. And question 5. Calculate the mass of the precipitate formed. Given the molar masses, capital M in gram per mole, for Pb it's 207, for nitrogen N it's 14, for potassium K it's 39, for oxygen O it's 16, for iodine I is 127. Answers. Before answering any question, we have to write our organization. First of all, we rewrite our balanced chemical equation as it is. Then we write the stoichiometric amounts. We have 1 mole for 1 PbNO3 taken twice, 2 mole for 2 Ki, 1 mole for 1 PbI2, and 2 mole for 2 KNO3. The given amounts are given, and here we have 2 given amount of the reactant. We are given 33.1 gram for PbNO3 taken twice and 16.6 grams for Ki. Question number 1. Calculate the initial number of moles. You have to know that the initial number of moles are the number of moles, small n, of the reactants. So, we just apply our formula. Number of mole of PbNO3 taken twice, it's the first reactant, equal to the mass of PbNO3 taken twice over the molar mass of PbNO3 taken twice. It's equal to 33.1 gram, it's given, okay, over the molar mass, which is 331 gram per moles, and it's equal to 0.1 mole. And remember how to find the molar mass. Molar mass of PbNO3 taken twice equals MPb plus 2Mn plus 6 times the molar mass of O equals 207 plus 14 plus 6 into 16 equals 331 gram per mole. And remember that the molar masses of each atom are given. while the number of mole of the second reactant, which is Ki, equal mass Ki over molar mass of Ki equals 16.6 gram of Ki, which is given, over its molar mass 166 gram per mole, and it's equal to 0.1 mole. And remember how to find the molar mass of Ki. It's simply equal to molar mass of K plus molar mass of I equals 39 plus 127 equals 166 gram per mole. Question number 2. Identify whether the reactants are in a stoichiometric or non-stoichiometric mixture. To see if the reactants mixture are in a stoichiometric or non-stoichiometric proportion, find the ratio R of each of the two reactants. So we have ratio of PbNO3 taken twice equal the initial number of mole of PbNO3 taken twice over its stoichiometric coefficient. So 0.1 over 1, it's equal to 0.1. And the ratio the ratio of Ki equal to the number of mole of Ki initially present over its stoichiometric coefficient, it's equal to 0.1 mole over 1, it's equal to 0.05. Remember that the ratio of each reactant have no unit, okay? So, since the ratio R of PbNO3 taken twice is greater than the ratio of Ki, therefore the reactants mixture are non-stoichiometric. Question 3. Identify the limiting reactant and the reactant in excess. Remember that when the ratio of the reactants are not equal, such that the ratio of one of them is greater than that of the other, the reactant mixture are non-stoichiometric, and hence there is a limiting reactant and a reactant in excess. So let's now identify which is the limiting reactant and which is the reactant in excess. Simply, since the ratio R of PbNO3 taken twice is greater than the ratio R of Ki, therefore 0.1 greater than 0.05, okay, 0.1 is the value of the ratio of PbNO3 taken twice, and 0.05 is the value of the ratio of Ki. Okay, so since the ratio of PbNO3 taken twice is greater than the ratio of Ki, therefore PbNO3 taken twice is the reactant in excess since it has the greater ratio. And moreover, since the ratio R of Ki is then less than the ratio R of PbNO3 taken twice, since simply 0.05, which is the value of the ratio of Ki, is less than 0.1, which is the value of the ratio of PbNO3 taken twice, so Ki is the limiting reactant since it has the smaller ratio. Question number 4. Determine the mass of the reactant remaining in excess. To determine the mass of the reactant remaining in excess, which we also call mass over left or mass unreacted, it's very simple. First, find the number of moles small n remaining in excess by just applying the following rule. And remember that here PbNO3 taken twice is the reactant in excess. So by applying the rule, number of moles small n unreacted of PbNO3 taken twice equals number of moles small n initial, which means initially found in the given of PbNO3 taken twice, minus number of moles small n reacted of PbNO3 taken twice. And remember that the number of mole reacted of the reactant in excess, which is here PbNO3 taken twice, okay, we always calculate it by using the stoichiometric ratio. So here we have number of mole reacted of Ki, which is the limiting reactant, over 2, its stoichiometric coefficient, equals number of mole small n reacted of the reactant in excess, which is PbNO3 taken twice, over its stoichiometric coefficient. Okay? And always remember that the initial amount of the limiting reactant is equal to the number of mole initially found of the limiting reactant is equal to the number of mole reacted of the limiting reactant. Why? Because the limiting reactant, which is here Ki, of course, is totally consumed, which means that the initial number of mole of the limiting reactant is totally consumed. So always we have that the number of mole reacted of the limiting reactant is always equal to the number of mole initially found of that limiting reactant. Always remember that. So now we treat the ratio. We have 0.1 mole over 2. 0.1 mole is the initial amount of the limiting reactant Ki, which is totally consumed, is equal to N reacted of PbNO3 taken twice over 1. Okay, so N reacted of PbNO3 taken twice, which is of course the reactant in excess, equals 1 times 0.1 mole over 2. It's equal to 0.05 mole of PbNO3, which have reacted, of course, by stoichiometry with the limiting reactant. And I will repeat always the number of mole reacted of the limiting reactant is equal to the number of mole initially found of that limiting reactant. Okay? Because the limiting reactant is totally consumed. Now, we can find the number of mole unreacted of PbNO3 taken twice. It's equal to the number of mole initial of PbNO3 taken twice minus the number of mole reacted of PbNO3 taken twice. It's equal to 0.1 mole, which is the initial number of mole of PbNO3 taken twice, okay, which didn't react completely, only part of it have reacted, minus the reacted part of PbNO3 taken twice, which is 0.05 mole and which we have just calculated by using the stoichiometric ratio. It's equal also to 0.05 mole. So 0.05 mole of PbNO3 taken twice remains in excess, remains overleft, remains unreacted, and hence will appear at the end of the reaction when it's over with the product formed. Now, when we have found the number of mole unreacted of PbNO3 taken twice, we can find the mass by applying the formula number of mole equal mass over molar mass. So the mass of unreacted PbNO3 taken twice equals number of mole unreacted of PbNO3 taken twice times the molar mass, equals 0.05 mole times 331 gram per mole equals 16.55 gram. And the molar mass of PbNO3 taken twice, we have found it in the previous slides. Okay. Question number 5. Calculate the mass of the precipitate formed. The precipitate formed is PbI2, lead iodide, and it's a yellow precipitate. And we can recognize that it's the precipitate from this small letter S, which is written at the lower right of the compound in a chemical equation. Note, always use the initial amount of the limiting reactant to calculate the amounts of the product, simply because the initial amount of the limiting reactant is totally consumed. Okay, and as we have said before, the number of mole initially found of the limiting reactant is equal to the number of mole reacted of that limiting reactant, simply because the limiting reactant is reacted completely. So by stoichiometry, we have number of mole small n reacted of Ki over 2, which is its stoichiometric coefficient, equal number of mole produced of PbI2 over 1, which is its stoichiometric coefficient. And remember that number of mole reacted of Ki, which is the limiting reactant, is equal to the number of mole initially found of Ki, which is the limiting reactant. So we have N produced of PbI2 equal 1 times N reacted of Ki, which means N initial of Ki, because as we have said, N reacted of Ki limiting reactant equal N initial of Ki, which is the limiting reactant, over 2, which is its stoichiometric coefficient, okay, equals 1 times 0.1 mole, which is the initial amount of, or the initial number of mole of the limiting reactant Ki, okay, it's equal to the number of mole reacted of Ki, as we have said, okay, over 2. It's equal then to 0.05 mole. So we have 0.05 mole of PbI2 produced. Once we have found the number of mole of PbI2 produced, we can find the mass by applying the formula number of mole equal mass over molar mass. So remember that to find the molar mass as well of PbI2, it's equal to molar mass of Pb plus 2 times the molar mass of I equals 207 plus 2 into 127 equal 461 grams per mole. So the mass produced of PbI2 equal number of mole produced of PbI2 times the molar mass of PbI2 equals 0.05 mole, which we have found by stoichiometry by using the limiting reactant, of course, and the ratio, times its molar mass, which is 461 grams per mole. It's equal to 23.05 grams. Okay? Thank you for watching my presentation.